Alrighty, let's make a start. Cool. So I got things up from where we left off last Tuesday, looking at the integration chapter review. Continuing to focus on the upcoming integration SAC for Term 3. So, unless there's anything in particular you wanted to have a look at instead, we'll continue on here, which would be 2b. Okay. We have a curve, x to the power of a half, that is the square root function. There's a point that exists along it such that you could create some sort of rectangle with the area, right? You've got point P, that'll have some y coordinate of capital N, some x coordinate of capital M. And it's very similar to the question in 2a, which was the ratio of 2 to 1. In this case, we're trying to prove that the area is 2/3 of the rectangle. So in other words, the yellow bit is 2/3 the size of the full rectangle. That's the goal. Very similar question to before. So with that in mind, we're going to more or less approach it the same sort of way. If we're trying to prove that one area is 2/3 the size of another area, well, one of the things that would be nice to do would be to figure out what are the area formulas for each of those areas. One of them is bound by a curve, the other is essentially just a rectangle. And so the rectangle area, quite easy, right? Just length times width. So we need to determine what our length is and what our width is. The length and width depends on where P is going to be, but more or less it's going to be distance from origin to M and distance from origin to N, wherever those end up lying. So if we go ahead and let me put do not disturb on. Okay. So if we go ahead and try to create our area formula for the rectangle, we would have area rectangle is length by width. If we give our point P an actual coordinate, let's say a comma f of a, so point P is going to be a comma f of a, and that's blurry. Let me change up the brightness real quick. And hopefully it actually stays. Has a tendency of dropping back down. So if our point is a comma f of a, then what we have instead is now going to be the square root graph for which there is the point that has a here and a height of f of a. So for the rectangle that we get out of that, we're going to have, let's call it a length of a and a width of f of a. So in other words, a times f of a. Finally, because we know this is the square root of x, or x to the power of a half, we can actually rewrite f of a purely in terms of a as its actual function. So finally, we get the area of the rectangle as a root a. Because if square root of x is the function, then if I shove in x equals a, I'm going to get root a as my y coordinate. That will get us our area formula for the rectangle portion. From here, we also need the area formula for the curve itself. So simply this bit there, excluding the whole rectangle bit. There's a couple of ways you can do that. One is significantly simpler than the other. Any thoughts on how we're going to get that? So it is an area starting from 0 ending at a that is entirely bound by the graph of square root x. So if it's entirely bound by a single graph, all we're doing is a definite integral there. So let's say area of the curve is integral from 0 to a of our graph square root x. Make sure you're putting in those dx's. We did see that exam report complain about people not putting dx's in there. All that remains now is figuring out how do we do a definite integral. Can anyone remind me the steps of how we do definite integrals?
And just integrate it normally, then we substitute the top and bottom numbers, and we do top minus bottom.
Yeah. So you would find your capital F of x, your antidiff of square root x, and then whenever you find that, you'll do capital F of top, which is a, minus capital F of bottom, which is not b but 0. There we go. So antidiff of the square root function. How do we do that?
We convert it to a fractional index.
Yeah, that makes it a lot easier to see what we would do. So square root of x is the same thing as x to the power of a half, which is now a power function. So it would simply follow the power function's antiderivative, which in this case is going to give us what?
Square root of x cubed.
Wait, no, yep.
Wait, yeah, square root of x cubed over
x cubed.
3 square root of x cubed over 2.
3 square x cubed.
Wait, yeah.
Okay, let me just think about that for a sec. So that would be, so x cubed root would become that fractional index. So what you would want would be the other way around there. So the rule is you increase this by 1, and whatever that raised power is becomes division. So rather than just putting whatever the raised power is as a coefficient, you divide by that coefficient.
Yep. Got it.
So yes, this is going to go to the power of 3 on 2, but then you basically, because that's a fraction, we're effectively going to flip that. And so yeah, if we now convert that to what it ends up being, it'll be 2/3 x power 3 on 2. And a nice little way of validating if we got it right would be, if I diff this, do I get back to where I started? Which you could imagine putting the power down the front and reducing it by 1. Power down the front is going to completely kill the coefficient, and reducing the power by 1 is finally going to get us to that power of a half. Joined a bit late, what question are we up to? We are currently doing 2b here. So very similar to 2a, where we're essentially comparing sets of areas and trying to prove a certain quality. With 2b, we're trying to prove the area of our rectangle, oh sorry, the area of the shaded bit is 2/3 the area of the rectangle.
Is the point P for A and B the same?
The point P, yeah, so the point P I've defined as its own little coordinate a comma f of a, just to make it something we can actually substitute some values into, rather than using capital M, capital N.
Okay.
Cool. Yeah, okay. And then yeah, finishing up our definite integral. Alright, yeah, just to recap the rest of it. So for those who joined late, we started by finding the area of the rectangle itself, which that's just length by width. And again, like I mentioned, setting our coordinate of a comma f of a, because it is a point that existed on that curve, we're able to get an expression for our rectangle purely in terms of one variable, a. What we're doing now is the area under the curve, which is doing our definite integral. We've currently done our antidiff portion of that. Now we're just doing the substitution of the upper and lower respectively. So that means our area of the curve is now going to be, so 2/3 root a cubed. Yeah, subbing in a for that, and then minus f of 0, so 2/3 root 0 cubed. You can use the fractional index as well if you prefer, which we will end up at least putting this one in there. 2/3 a 3/2, and then this one's just 0. And if we look at what we've got now, we have our area of curve, which is 2/3 a to the power of 3/2. We have our area of rectangle, which is a root a. We got to do something to make these more comparable, such that we can prove one is 2/3 the other. We can see the coefficient 2 on 3, so that's a pretty good sign that we're on the right track, but the way that both of these are written makes it slightly hard to see that these are, in fact, the only difference between them is that 2/3. What would I do to rewrite this in such a way where it is more obvious that one is 2/3 the other? There's a couple of ways you could go about it. Either making the a root a look more like the other area formula, or rewriting the index to look more like the rectangle one. Both is perfectly valid. Can anyone suggest a way that we could do either of those?
We can put the a inside the square root of a of the AR.
The AR, yes. Okay. So the way you would do that, there's this implied index of 1, and with the root there's the index of a half. So if we think about the index laws, 1 plus a half gets you to 3/2. So this is just a to the 3/2, whereas this is 2/3 a to the 3/2. So if you directly compare them, AC to AR, AC to AR, you now have 2/3 a 3/2 ratioed with a 3/2, which of course these will cancel out, finally giving you your ratio 2/3 to 1. Now, as far as you giving your final answer, you don't have to do that. It's sufficient to get to this stage here and then have a final statement that says, therefore, AC is 2/3 AR, or so on and so forth. You can put that in words. You don't have to go ahead and do what I just did there, but I figured it'd be nice to touch on some more ratio stuff, given that's where we left off last time with 2A. Okay, so I guess to recap the whole solution there, just so everyone can be on board at this point, it was a matter of trying to prove that one area was proportional to another, more or less. So when you're trying to do that, best bet is to start by finding both those areas. One was a rectangle, so we just did a rectangle equation. The other was a curve, so we did our integral. Once we had our two values, we can now directly compare them and see to what extent are they proportional by directly comparing the results of one to the result of the other. Key thing to highlight here is, like in part A, you are allowed to introduce your own variables into the equation to make life a little bit easier. You'll notice I didn't use the capital N or the capital M in my version of the diagram because yeah, it's using more variables than you need. The ideal is to get everything down to single variables so that they can either cancel out or at the very least become more directly comparable. If there's any questions about that, feel free to let me know. Otherwise, have a think of part C, which looks like it's going to be a bit of an ordeal. Okay, so 2a, 2b, we were looking at x to the power of something. Now 2c, we're still doing x to the power of something, but that something is now an unknown. we have PM and PN, which are perpendiculars from some point to the x-axis and y-axis respectively. That's interesting. Look, question. Does C assume any knowledge from A and B? Maybe. Some of the knowledge that we've obtained, or at least the working out that we've done, might be similar. I haven't actually had a read of C, but just by, as in the working out, probably not. Probably not. Because this one's got 2 to 1, this one's got 2. Well, no, 2 to 1 actually is 2/3. Yeah, in a sense. I don't think it's like necessary to have 2A and 2B, but it definitely helps because both of these are actually the same question now that I realize it. A ratio of 2 to 1 is 2/3 per thing. Like we literally had that written out as the ratio at the very end. 2/3 to 1. And if you wait, is that right? No, sorry. It's got a similar idea to it. Anyway. So now we have a generic x power of n. PM and PN are perpendiculars. So in other words, it's going to be the same idea that we have in 2A and 2B. If you look at those, NP is perpendicular horizontally, PM is perpendicular vertically to x. So that's what they mean by the perpendiculars. Prove that area enclosed by PM and the curve is equal to n+1 of the rectangle. Okay, so it is basically the same sort of question, but now the powers are unknown. Because it's the same sort of question, we'll do the same thing as last time. So let's just be clear on what it's actually asking. Prove the area of the region enclosed by PM. What exactly is PM? Well, PM would be the vertical bit. Enclosed by PM, x-axis, and curve. So that would be the yellow bit that would exist in part B. That's the equivalent of it, because it's enclosed by PM, the vertical line, x-axis, the horizontal line, and the curve, the red line. Whether that red line is concave down or concave up is whatever. It's still going to be the roof of the shape. Whether it's concave down or concave up depends on what this n ends up being, but it will be one of the two. And prove that's equal to some proportion of the area of the rectangle. So again, area of rectangle. So, with that in mind, can anyone suggest how we might start this one out? The steps will be largely the same, but what it looks like will be different.
We try to find definite integral of that curve between 0 and m. Wait,
Yep.
no.
Yeah, 0 and m sounds about right. That'll give you the upper bound of the
If
curve.
the intercept is not at the origin,
Say again.
then what if the intercept is not at the origin?
Well, it's x to the power of n, so there's no horizontal or vertical translations. So we're pretty much guaranteed to have an origin regardless of what the n actually is. But good checking out, right? It's good to validate these things before you make assumptions like that.
Yep. Okay.
So yeah, 0 to m.
Definite integral of x to the n.
Yep.
Between between 0 and m.
Yep, between 0 and m. Perfect. That'll get you the area of the curve, which I'll write as AC. Yeah, might as well follow this thread. So again, from before, we knew definite integrals as a matter of anti-diffing, and then doing capital F of top minus capital F of bottom. So first step, capital F of x. This one honestly will actually be a bit easier to anti-diff, now that it's just a single letter in the top. What's my anti-diff going to look like here?
X to the n+1 over n+1.
x n plus 1 over n plus 1. Perfect. In fact, that is literally exactly what's written on your formula sheet, which is why this one ends up being easier rather than harder than the other question. Yeah. Then from there, finishing off our definite integral, we want to do our capital F of m minus our capital F of 0. Capital F of 0, just looking already, 0 divided by anything is still just going to be 0, so long as n is defined. In fact, yeah, I wonder, did they give any constraints on n? They didn't. That's interesting. Because if you had like n equals -1, well, this antidiff wouldn't hold. I don't think they were intending us to think too hard about that in particular, but it is worth pointing out that like if you're trying to prove this particular circumstance, realistically you do also need to consider the case of n being -1. Because if n is -1, this antidiff doesn't actually hold. This is where you would do the logarithm antidiff, because n being -1 would mean you'd have 1 over x. So I wonder if you do have to do two separate proofs. One for the this version of the antidiff. So as long as n is an element, oh yeah, as long as n does not equal -1, and then also this version where n is -1. Well, we'll do the one that I think they intended first, and then we'll see if we could also prove that this antidiff as well. That'll be the most complete answer, but I kind of doubt they were expecting us to do that. Anyway, finishing it up, so capital F0 just disappears, so all we really need to care about is capital F of m, which is going to give us area AC, where we have capital M n plus 1 over n plus 1. I'll save a spot to do this one as well later, but that can be a bit of a side quest after we do what is probably going to be the main solution to this. So far we've just found the area under the curve portion. We need to compare that to the area of the rectangle, which means we need to know what the area of the rectangle will be. So, how are we going to get our area of rectangle? You can use the image in part B to help out, or even part A. They both more or less help the exact same way. Well, generically we know the area is length times width, so we just need to look at our picture and figure out what's the length, what's the width. And from there we'll try to get everything in terms of a single variable, ideally m, because we've already used m in the curve equation. So if we look back at our figure in part B or even part A, we can see that horizontally speaking is from 0 to m, so just m, and vertically speaking is from 0 to n, or just n. So our generic area formula would be m times n, whatever that is. Problem is, that's two variables, we would like one instead. So the way you pretty much will always do this for these kinds of questions where you have a curve and areas inside of curves or areas related to curves is because they intersect with each other, you're able to rewrite things purely in terms of x coordinates by subbing in what your x coordinate is. So if you look at like the figure of 2b, the coordinate m exists on the curve and it gives a y value of n. So assuming m was like 2 for instance, if I wanted to figure out what n was, I would shove 2 into my function and then whatever came out of that would be the y value, because that's how it works. Y equals f of x. You shove x's into it, you get y's out of it. So rather than do mn, it would be m comma f of m. Well, m times f of m. Let's try that again. M f of m. And then the final simplification would be using what f of m actually is. So if f of x is x power of n, then f of m would be m power of n, which we can use our knowledge from last time to use a bit of index law stuff to convert this to m n plus 1. Yeah, because when they multiply across, the powers add. We've now got area of rectangle. We've also got area of circle. If we look back at what we're actually trying to do, it says prove the area of the region enclosed by the curve is 1 on n plus 1 proportional to the area of the rectangle. Well, here's our 1 on n plus 1, and here's the curve itself. So again, if we do the ratio AC to AR, comparing the two, you've got 1 on n plus 1 of m n plus 1 m n plus 1 comparing AR and AC. From there, these are common factors, so you now have n plus 1 to 1, or 1 on n plus 1 to 1. So yeah, the whole of question 2 was more or less just getting you to go through and be like, hey, here's how you compare things. Here's how you do the same sort of question with different numbers, and then finally generically across the board. That's the intended solution that they want you to do. Just for fun, I am going to go back on that logarithm bit because they didn't constrain n, and I want to know if that was their fault or if they wanted us to actually go ahead and do the logarithm bit. So as a reminder, this antidiff only works if n is not equal to -1, and so if it is -1, that's when you get the logarithm, because this becomes 1 over x. So let's see if the same thing actually comes out to play. Capital F of m minus capital F0 would be natural log m minus natural log 0. Natural log 0 is 1. Where would you go from here? Because that would be it. That's the whole area. That's also AC. So how do we then compare that to that? The answer probably you don't. So I have a suspicion they didn't intend that. They intended to have n being, I guess, just some positive number. Let me have a look. Do they have anything in the answers regarding this? Yeah, they fully ignored the whole n being -1 possibility. They just did the antidiff that we saw and expressed there. So no worries then. Okay. Next up, question 3a. Area enclosed by... Oh, that's actually kind of fun. Area enclosed by x squared and y squared equals x. Two separate things there. That's kind of funny. Yeah, let's go ahead and do that. The obvious issue there is you got a y squared equals x, and we've got to figure out what the hell that means. So area enclosed between the parabolas just means first we've got to figure out what we're looking at. So y equals x squared would be that, and y squared equals x would be that. From there, we can see that the only thing that actually has a bound area is going to be in here. Everything else is unbounded. The lines will never close up, so we never have to worry about that, so on and so forth. So when we're considering our bound area, it's exclusively going to be from 0 to wherever these intersect. And we know the graph of y squared equals x is on top of the graph of x squared for the entire duration, no matter what. Only challenge now is how do we anti-diff this when we don't have two functions that are y equals something, which is what we normally need for our definite integral setup. What might we do to get that? So, just for context, let's say the intersection point is at A. You would want to do function 1 minus function 2. So function 1 I'm considering the green one, function 2 I'm considering the red one, because you're doing a top take bottom integral. Only challenge is I can't just do x squared minus, x minus x squared, because the functions are not both y equals something. If you were in my classes before, we briefly touched on the graph of y squared equals x, and we did it for a very specific reason. It was to show where another graph that we use a lot comes from, and it explains a bit of weird behavior from it. The graph that it explains is the graph of square root x. So if you think about this as an equation rather than a graph, y squared equals x could be rewritten as y equals plus minus root x. That's the rearrange. You would square root both sides. Positive root is the one that's on top, negative root is the one that's on bottom. So rather than use the whole y squared equals x and try to figure out what you're going to do to integrate with that, instead convert it to, well, an actual y equals something, and then make this an actual function. So for context, this isn't actually considered a function. This is considered a relation. Difference between functions and relations? Well, maybe I'll let someone tell me. Does anyone remember the difference between a function and a relation?
Function has to pass the vertical line test.
Has to pass the vertical line test, absolutely. So in other words, if I draw a vertical line anywhere on the graph, it should only touch it once. In the case of the green one, it touches it twice. Now that's a shorthand. In reality, it just means if I plug in a value of x, I should only get one value out. One in, one out. With the graph of y squared equals x, I get two results. So to convert it into a function, I only need to care about either the top or the bottom portion. If the top portion is the thing that has the area, then I'm only going to care about the top portion. So my integral now becomes square root x minus, because it's top, square root x, minus the bottom, which is graph of x squared. And we're doing that from 0 to a, where I'm saying that a is whatever that is. Now that we've simplified what our function actually is, well, turned our relation into a function, we can now continue on with the rest of this, which is figuring out how to evaluate this. We needed an exact value, and a was just a placeholder. How would we find a in this circumstance? So we want to find the upper bound of our integral that we would be doing for bound area. That's alright. So if a is referring to this intersection point, actually let's take a step back. So to do bound area between curves, one of the first things you want to do is first draw this picture. Identify where do you actually have bound area. So that's already done for us at this point. The next step is you want to figure out how far horizontally does that area span. In this case it goes from 0 to wherever this intersection point is, which I've labelled A. I've labelled it A, it actually has a value. Right, we can find that. Because it's an intersection of curves, we're going to make the curves equal to each other, thus finding the actual value of it. So you have the graph of square root x is equal to graph of x squared. You can handle this a lot of different ways. I'm just going to square both sides. X equals x power 4. And what you want to try and do is avoid the temptation to just cancel x from both sides. Because while that does give you a solution, it ignores the possibility of x being 0. Because in order to actually do that, you have to divide both sides by x. And if x could be 0, what you've actually done is technically invalid as far as math is concerned. It still gives you the solution you want, but if you care about all the valid solutions, what you would do instead is a factorization approach. Bringing all terms on the same side, factorizing out, and then null factor law. So you now have x equals 0, like we expect, and x cubed equals 1, which finally gets us to x equals 1. Which makes sense what we had, right? We knew they were going to intersect at the origin, and in this case, we figured out that a is 1. So with that in mind, we replace a 1 with that, and we're just going to do our antidiff and definite integral from there. So, antidiff, first things first, rewrite this as power of a half so we know a bit better for how that antidiff actually works. Raise the power to 3 on 2, divide by the power, and same thing over here, divide by the raised power. From there, definite integral from 0 to 1. So let's do that. Capital F of 1 minus capital F0. Quick inspection, capital F0 is just going to be 0. If you shove zeros in those spots, it all disappears. So really we just care about capital F of 1, which is now 2/3 minus 1/3. Again, putting 1s there basically just leaves the coefficients, leaving you with 1/3 for, what do we even do here? It just said find area enclosed. So yeah, I guess you just say area equals 1/3. So yeah, probably the only challenging part about that was converting the relation to a function. Everything else was a very standard area bound between curves thing. Next up, we're going to do the exact same thing, but generically now. Show the curves with x power of n and y squared equals n, no, y n, y to the power of n equals x. There we go. Bit different though. We're not doing the actual area, more so proving that they always intersect at 1, 1. Bit different. So we're not going to go full tilt what we just did there, but we are going to do a lot of the same steps. Did I draw my picture? I did. So the cool thing, yeah. Okay, let's have a think. So when you have y equals x power of n and yn equals x, or in other words, y equals plus minus nth root x. Maybe I'll just do 1 over n. x, 1 on n. When you're comparing these two things, you more or less have two possible outcomes here. Actually, in this case it's 3, because they've included n equals 1. So let's have a look at them all. So for n equals 1, you just have y equals x, and you have, well, also y equals x, but you have plus minus x in this case. For y equals x, oops, missed it. Y equals x, you have that. For plus minus x, you have that and that. Now, that's really strange. I don't think, again, they meant n equals 1, because unless I've done that wrong, they do not intersect at 1, 1 at all. What the hell? What happened? If n is even, x equals 1 is the only solution. Okay. Yeah, unless I'm, again, mistaking something, I don't think they intended n equals 1 to be part of this. Well, maybe... No, actually that's still fine. It doesn't mean that they uniquely intersect at 1, 1. It just means that they intersect at 1, 1, which this still does. So for y equals x, this one, you have just this line. For y equals plus minus x, you still have this line, but now also this line. And 1, 1 does actually still exist there. It's just not a unique solution to it. Okay, cool. More importantly, they were looking for us to explore the other two options, which is n being even and n being odd. If n is even, the graph of y equals x to the power of n is going to have a very particular shape. Can anyone tell me what type of shape x power of n would be if n has to be an even number? So think x squared, x power of 4, x power of 6. All those have the same kind of shape. What do they kind of look like?
Focus, what did you say? I just cut out.
Just cut out, that's fine. So we're basically exploring, it told us to prove that the curves with xn and yn equals x, they all intersect at the same spot. So what we're doing now is essentially exploring the options. We looked at n equals 1, now we're looking at what happens if n is an even number. So specifically for y equals x power of n, if n is only allowed to be even for that, well, I guess positive even. Yeah, we'll say positive even. What's the overall shape that it has to be? Think x squared,
kind
x
of
power
like
4.
a symmetrical, like parabola type.
Yeah, it's going to be parabola type, absolutely. The degree to which n is raised, the more positive it gets, the steeper that parabola shape will be. But it still maintains a parabola-like shape.
Yeah, it just becomes more narrow, right?
Yeah, precisely. So like, let's say this is x squared. This one would be x, I don't know, 8. It gets kind of thinner and shoots up a lot faster. So that's for the first graph.
Yeah, and then for odd ones, it's just like your cubic shape, right?
Yeah, that's right. So if we were to go ahead and do n being odd, then yeah, for that exact same graph, it would be cubic-like.
Yeah. Does that follow through for every odd number, like 5, 7? I think it does, right?
Yeah. Not the negatives though. Just
Okay.
the positives.
Yep.
Yeah. Now that gets us the first graph. We got to also compare to the second graph as well. So now for the evens, again, plus minus x power of 1 over n. Now if n is even for that thing, what's that going to start looking like? These are a bit harder. So to maybe give you a better idea, if this is easier, it's plus minus nth root of x. So that could be the square root, could be the fourth root, could be the sixth root, so on and so forth. That also has a very specific shape. Any takers for that? Easiest way to think about that, if I'm saying that they all have the same shape, there is at least one of those graphs that you know, which is the square root graph. So if I'm saying that the square root, the fourth root, and the sixth root all have the same sort of shape, then as long as you know what the graph of the square root looks like, you know what the graph of the other roots look like. So if the graph of the square root is normally this, or the plus minus version of it is this, then any increasing n that is even is still going to have this overall shape. Again, just getting steeper as n increases. So this is what we have when n is even, and we're hoping that, or we're proving, that they're going to both intersect at 1, 1, always. For n is odd, you can pretty much already, well hopefully by identifying the sort of overall idea, figure out what's going to happen if n is odd. You now have the cube root or the fifth root, or so on and so forth. Cube root graph, for those who weren't aware, still has the root kind of shape, but it now also has a negative tail to it as well. Hopefully, still has that 1, 1 coordinate. Yes, it also intersects down here at -1, -1, but as I realized, we're just caring about the 1, 1 coordinate. It's not saying that it's a unique solution, just that it is a solution. So to have the most complete possible answer, we need to prove that all three of these things are true. For n being 1, there's really not much else to say. They literally exist on the same line, so as long as y x to the power of n has 1, 1, then in fact, let's just do it. So we have y equals x power of n. If we shove in y equals 1 and x equals 1, we get 1 equals 1. Yay. Same thing over here. Y power n equals x. 1n equals 1. 1 equals 1. Yay. We both get trues. For here, n being even, things get a little bit more complicated. Because now we don't have a value that we're subbing in necessarily. What might we do to now go about proving this one, that n equals even? We'll take it a bit of a different approach. We'll use the same sort of idea that we talked about when finding our bound area. When finding our bound area, we wanted to figure out where the curves intersect. So rather than subbing in coordinates of 1, 1 and trying to say that they both fit there, we're going to take a different approach and just make the curves equate to each other and go from there. So if we again simplify it down to just the root bit, because we only care about the positive root, we now have x1 on n is equal to xn. Right, because remember this is xn and this is x1 on n. From there, we solve it the same way we did before. So if we get everything to the same side, we have xn minus x1 on n, and then finally it's a factorization approach here to finish it off. So for that, the most you can take out is x to the power of 1 on n. Let me think about this, because that's going to get us something minus 1. And if I expand it through, multiplication is addition, so... Oh shit, what's this look like again? 1 on n plus what equals n? X equals n minus 1 on n. X equals n squared minus 1 on n. Expand that one out so you get the same denominator. Jesus, yeah, okay. N squared minus 1 on n. So if I expand that through, plus 1 both sides, yeah, that'll get me down. That's a funky thing. So to explain what I just did there, because I kind of just went on my own little tangent to get that. When factorizing, you want to figure out what's the biggest thing you can take out of both of these. Now, for any positive n, this index will always be bigger than this. Right? If you have n is 1, well, like let's just say greater than or equal to, right? Because if n is 1, they're both the same. If n is 2, you now have x squared and root x. So every increase of n, this is always bigger than that. So when seeing what's the biggest thing you can take out, you got to take the smaller one out and then figure out from there what the what remains over. Now, how I figured out what remains over is essentially thinking about it backwards, which is, okay, I know I want to take out x power 1 on n. That's going to leave me with the -1 from this, nice and easy, but I don't really know what that index is going to be. In order to figure out what that index should be, I want to figure out what number is such that when I expand this through, I get back to n. Or in other words, using my index laws, if I do 1 on n plus this, because that's how indexes work when they're multiplying, they add 1 on n plus whatever this is, which I just called x, should give me that. That's where I created this statement here. From there, if I just solve what x is, I know what my power should therefore be. I can appreciate it's probably a bit confusing that I've used x, so maybe I'll use a instead and call that a, just because we already had x's in here. So I just said, okay, I don't know what this is, let's call it a. A must conform to this in order to make this factorization work. So solve for a. Is it clear enough what I did there? Because that'll be the most confusing part of this, almost certainly. Okay. From here, it's now null factor law. So you now have this equals 0 or this bracket equals 0. 0 equals x 1 on n. This is just going to be x equals 0. Doesn't matter what this is, you just do the opposite to power both sides, giving you x equals 0. The other equation is the nastier one, x n squared minus 1 on n minus 1 equals 0. So this set of brackets equals 0. From there, add 1 to both sides, x n squared minus 1 on n equals 1. And the good news is, it doesn't really matter what this is, whether that evaluates to 2, 3, 4, any of the negative numbers, whatever, you're still just going to do the opposite of that to this. And the good news about 1 is that whether I square it or square root it or whatever, it's just going to stay as 1. So I don't really care what this thing is, I just do the opposite of it, giving me x equals 1. That gets us our two possible x solutions, one of which is the one that we care about, which is to prove that they intersect at 1, 1. Or at the very least, we've proven that x equals 1 is part of the solution. All we need to do now is prove that y equals 1 is the corresponding portion of this. And that is pretty trivial. You can look at either of these graphs and prove that. So if you have the graph of xn, for instance, if I shove in x equals 1, I get y equals 1. Therefore, 1, 1 exists. You know, I came into this sick and I was like, I wonder if I can do harder math. And then I just did this. So, I hope that makes sense. Is there anything in there that needs further clarification? Like, the actual steps there are stuff you guys have always done. It's just that we're using, like, a lot of letters in it now, and so it might look a bit worse. I know a lot of people will get a bit confronted by this.
Do you think it's best practice, like in a SAC, just to like define everything?
Oh, for sure.
Like even if it takes time.
Yeah. So like, even if it takes time. Yeah, I guess. It depends on the extent.
Something for me was that like, because sometimes I can't really bother to have like you know write out the work. But I guess if you define it, it's just kind of there, so you can just check it. You don't have to look back to the question every time.
Yeah, I guess it depends to what extent you're looking to define things. Like for instance, I went ahead and drew graphs to depict all the possible scenarios. I wouldn't necessarily call that defining something, but I would say it's probably a good idea to think about your possibilities. And then from here, I didn't necessarily define what A was. I kind of just used it as part of the solution set. So you might want to do that I was verbalizing what I was doing, so that's why I could kind of maybe get away with it. But if you're doing this sort of stuff, maybe you would do a sort of half step here, which would be like 0 equals x1 on n bracket xa minus 1, and then do all of this, and finally put in what a should actually be. I'm not writing a statement that says let a be the index of x, I'm just putting it in there and then doing some math with it to get what that is. So yeah, I would say it depends on to what extent you're expecting to define things. If you're doing it more or less what I've just described here, then that's, I think, a good idea. If you're going to go ahead and define like let a equal an index, you're probably spending a bit more time than you need to, but it's also more clarification, so it could just help you with your solution, being more clear with what you're actually doing. So yeah, I'd say more information is always good. If you need it to get your head around the question, then do it. Yeah, and the good news is this solution set that we just did here had nothing to do with n being even or odd. That just works out. And so that applies for the n equals odd solution set as well. So in reality, yeah, we didn't need to really think about, at least in this case, whether n was even or odd. We just did it. But it's still a good idea to explore your possibilities. Like, for instance, the logarithm possibility for this question here. They didn't actually define that n could not be a -1, and so logarithms come up and suddenly you can't really compare the two. So if the question was written better and had a way to compare logarithm version as well, then that would be something you should consider. So, you know, sometimes doing all this sort of getting your head around it doesn't necessarily always pay off exactly as part of your solution set, but it's something you should definitely consider regardless, which is, what are my possible options here, and then do these sort of condense into each other? Do I have to care about more than just one of these options? Like, for context, the only thing the book gave was this. They didn't do any graphs of what happens if n is 1, what happens if it's even, what happens if it's odd. They just went straight for the throat and just said, cool, make them equal each other and see what happens. Which, if you know what you're doing, is what I recommend. You don't have to do this stuff if you already know in your head what you're going to do. That's just wasting time. But I know for pretty much everyone who's doing this sort of stuff for the first time, this is very valuable to do, at least in your practice, at the very least. Okay. We're about to hit time. Let's see what we can do. Part C, show that area between the curves is that. So I imagine this to be a very similar kind of question, just stuff we've already done. Area contained between the curves, if you have a look back at the screen share, you'll see that xn is always on bottom to the root. And so you'd always do the root version over the quadratic kind of shape, or I guess the parabola. No, not even that. It'd be the power function. No, they're all power functions. You know what I mean. The quadratic looking shape there, and the root looking shape there. Now, proving the area contained is equal to that. Yeah, okay, why not? Still going to be a top take bottom. And we're still going to use the simplification of the root itself rather than using the full, what's it called again? Relation. We already went through efforts to prove they intersect at 1, 1, so we're going to go ahead and set our boundary 0 to 1, because we already know that's going to be what it is. We have the root on top, so x n, 1 over n, sorry, and we have the the power function on top, so that means minus, so it's top take bottom dx, anti-diff from here, which just because we're running low on time, I'm just going to cas that out. Anti-diff of x1 on n. We've done both of these before anyway, so hopefully this shouldn't come as too much of a shock to what the actual antidiff would look like. So that's that. Come on, load. That's those antidiffs. They've done a bit of a weird factorization by... Wait, no they haven't, sorry. That's totally fine. That becomes our antidiff, and then we'll just do top take bottom. So it would be... Obviously in the CAS you'll do this differently. You'll just do the definite integral, but if you're doing this by hand, you'll do your top, which is the 1, minus the bottom, which is the 0. Ah, Jesus, of course it doesn't simplify. Really? Why do they stuff up? Okay, well that should just be 0. That should also just be 0. I don't know why they're staying alive. And if that's 0, that's 0. Let me finish this off then. So I don't really know why the CAS gave us that, but we have negative bracket n bracket 0 minus 1 minus 0 plus 1 over n plus 1, which finally is going to get us negative n for that, plus 1, n plus 1. So it's going to be n minus 1, n plus 1, which is what we wanted to have happen. So I guess the CAS had something to say about this. Maybe this goes undefined at some spots. Probably does. Maybe it's non-real actually. I don't know. Something's weird about it. Point is, it does get us there. Cool. That's about it for today. If there are any further questions, feel free to ask them, and I'll do my best to stick around and help you through it. If not, thanks for coming.
I've got a question that I was doing in my worksheet.
Yeah?
Could you just give me a second? I'll just grab my worksheet.
Yeah.
Thank you.
Yeah, no worries. Take care.
Hey Chris, I also had a opt-in to help. I also had a question about a specific question as well.
Cool.
If you had time.
Yeah, we should. Let me just check my phone. See if I've got anything to do. I've got to pick someone up from the train station, so let me... Yeah, no, I should be fine.
Cool. Thanks.
But yeah, just like, I guess for later reference, if you do know ahead of time if there's a question you want to have a look at, put it in the
Yeah,
Google form.
Yeah, I just thought of it like right now.
Yeah, no, you're good. Yeah, Nihal, I think you said you had one.
Okay, so the question is, this one's an MCQ, but yeah. So the tangent to the graph of y equals to x cubed minus ax squared plus 1.
Hang on, let's just get the function first. So, remind me what the function
is. X cubed minus ax squared plus 1.
A x squared plus 1. Yeah, tangent to this.
Yep. Tangent to that at x equals to 1 passes through the origin.
Oh, yeah, okay, I know what this is then. Yeah, so passes through origin, shove 0, 0 in as your, oops, that's not how that goes. Shove 0, 0 as your x and y for that. Solve for A. A is going to be 1. Is that one your multi-choice?
Yeah.
Yeah, so that one, you just create a generic tangent line formula, and because you have y equals mx plus c, you just shove in a y and an x, and you'll get your whatever the leftover coefficient is.
Okay.
I've got this explored in the tangent line notes. There's a version of this question written out fully.
Okay.
Cool.
How do you use the tangent line function?
Yeah, so that's just in the calculus menu. Whoops, that was way too fast. Calculus menu, tangent line, and the syntax of which is to do function, comma, x, comma, where you want to take your tangent line at.
What's the second value for?
Good question, actually. I don't really know why it's there. It doesn't seem to change, but basically it's just saying, kind of like how you solve comma x. It's like saying the thing that's following is an x value, not a y value. So it's saying h of x, x, and then x equals 1. Yeah, I don't really know why that second input's there. I should just assume you're subbing in an x, but it's there, so yeah.
Alright. Yeah.
Cool.
Don't think I have anything.
That's about it?
else.
Awesome.
Oh wait, no, there's one more question.
Oh yeah?
Yeah, there's also an MCQ. So the average rate of change of the function with rule f of x equals to x cubed minus square root of x plus 1.
Square root x plus 1. Okay, the average value of this.
Between 0 and 3. Between x equals to 0 and x equals to 3.
And that's
Yeah,
it, just find the average value.
Yeah.
Yeah, well that's an equation.
For some reason, my answer does not match any of the options.
Alright.
I got 187 over 36, and the options. Well,
yeah, what's the
it's not there.
what's the interval again? 0 to 3?
Yeah, 0 to 3.
So it's a third times the integral of 0 to 3 h. And that wasn't one of them.
Yeah. So the options are 12 and okay, so 12, 25 over 3, 26 over 3, and 8. So yeah.
Yeah, that should be busted then. If it's definitely from 0 to 3, then this is how you do average value. Where was this sourced from?
Ed Rollo.
Ed Rollo.
Ed Rollo, chapter 8, chapter check. Check enable.
Yeah, I'm convinced you did it right. I don't see what's wrong with that. So that might just be an error on their part.
Okay.
Yeah. Hard to follow up with them, of course, but if you're doing average value, that is average value. Wait, sorry, did you say average rate of change at some point?
Yeah.
Oh, average rate of change. Yeah, that's different. That's rise over run. This is average value. Rise over run is average rate of change. So that is instead h3 take h0 on 3 take 0. Was that one of them?
Oh yeah.
Yeah, okay. Average rate of change is not average value. There we go. That's what was wrong. Cool.
Yep.
Alrighty. Taihan, what you got for me?
Yeah, do you remember the worksheet I sent you a while back? Do you still have that?
The practice sec?
Yeah, it was like the integration worksheet. You want me to send it again?
No, I got
think
it.
I sent you two in the school.
Yeah, show me.
Yeah.
I've got the screen share up still. This is it, yeah?
Yep, that's the one. Do you have like the file? Because I was a bit unsure about the last question. But I think
Oh, is it this one?
if we'll have enough time. Is that something we can maybe cover at the next one?
Is it this one?
No, just like from 2019 and 20.
19 and 20.
Yeah. But either one. Is...
I mean, that is a lot.
Yeah.
I think...
Can you just give me like a quick overview, because I just wasn't sure how to approach it.
Yeah, I think I can do better than that actually, because I think at least one of these I got a full work solution for. So 2018 exam 2
because
solutions.
you've done these questions before. I forgot.
Yeah, I've put the I haven't fully finalized this one. It's still a Word doc, so I don't know if I haven't even opened it up. Let me see. I'll definitely check
Wait,
if
so
this has.
do you have like, because it says you have the work solutions for the exams, right?
Yeah, for definitely the most recent ones. Let's
Okay.
see, is this one of them?
Yeah, exam solutions. Yeah.
Did I have it?
So you've done it up to 2020 exam one, I think. That's what I can see on the classroom.
Yeah, which is why this one's still a Word doc. It's not quite finished. It doesn't actually. Yeah, it doesn't have that one.
Yeah, that's all good.
Okay, so what would I do for this? Hence or otherwise? Oh, this one actually exists on the textbook as well.
Oh,
This-
really? Okay, maybe I'll have a look.
Yeah, have a look at that
That-
textbook with
Yep.
the bound area stuff. It's got to do with the fact that you can't by hand anti-diff this log. And
Okay.
so you got to use the inverse relationship. So effectively finding this bit of area and then flipping it downwards will help you get that.
Okay.
As for the... I could have sworn we'd done something very similar to this.
It was
Ending,
more the last. It was more the last parts, like C and D.
well, C you can ignore because it's got the matricy stuff.
Oh, okay.
There is
that's right. Isn't that special? Like,
well, it's special now,
or is
but
that
it
just
was
not in the study design anymore?
yeah, exactly.
Oh,
It's
okay,
not in
that's
the
why I
study
was
design
confused. I
anymore.
was like, I've never seen this before.
Yeah, you can knock off C. There is a way to convert it into the X dash Y dash stuff, but it's worth just ignoring, I think.
Yep.
And then D 0 to 3 pi L.
I just need to know like how to approach it, and then I think I can.
Yeah, I'm just giving it a read firstly. Okay, so it's just tangents firstly, and then it's saying what are we actually trying to find? Total area of shaded regions. Yeah, okay. First thing would be only finding one of the top or the bottom and then doubling it.
Yep.
So let's say we're only looking at the top here. We've got two curves that matter. We got F and G, so there's got to be a slightly better way of doing this. Rather than just do this slice, and this slice, and this slice, which you could.
Yeah,
it would
I
just
mean, I
take a
was
while.
thinking about doing it that way, but I was like, there has to be a different way.
Yeah, let me pull up, this was 2018 VCon 9, let me pull up the exam report. Let's see what they did. Which one was it? What's it say in the corner? My toolbar's in the way. Ah, question 20. Wait, what? No, that's their thing.
VCon 9 says.
VCon 9, what does that even mean?
It's all good if not. I think might have time on Friday.
Oh, yeah, okay, no, I think it's this bit here. I think it looks like earlier in the expression, or earlier in the questions, you find out how to, my light is crashing. I don't know if I'm losing power or something. But it looks like earlier in the question you create an expression that is the difference of the two functions. And when you difference the functions, I guess you flatten out these bits, and then it's a matter of just integrating across the difference.
Okay.
That's what they're doing. I'd have to look into it deeper to know why that works, but that's what they've done. So maybe if you were to do these, it might be a bit more illuminating as to how you can simplify things further. But I guess just know that you can do this slice, this slice, this slice, this slice, and double it all up. And
I'll
that's
just try
doable.
like that and see what I get.
Yeah, that should be doable.
Awesome.
Cool. And I guess let me know how you go with that. If you still need more support with it, we can attack it on Friday.
Sounds good. Thanks, Chris.
Awesome. I'm going to leave and hopefully not fry out my circuit board because apparently my lights are flashing.
You're looking funny on the camera because you're like appearing and then disappearing.
Oh dear. Alright, I'll sort
Yes,
that
yeah.
out.